Good morning, everyone. Today with us, it's a pleasure for me to have Elisa. Elisa Fevola is a PhD student at Politecnico di Torino, and today she will talk about optimal control for boundary conditions estimation in cardiovascular modeling. Thank you, Elisa.
Thank you, Maria, for the introduction, and thank you for the invitation. So for those of you who don't know me, I'm Elisa Fevola, and I'm a PhD student at the Electronics Department at Politecnico di Torino. But for my PhD, I'm collaborating also with the University of Toronto and with the MATLAB group at CISA. So today I will present to you a framework that I have developed for my PhD that is based on optimal control, and it is used for estimating boundary condition for cardiovascular models. So a first question that you may ask is, why do we need cardiovascular modeling and why are we interested in this? So the main reason is that cardiovascular disease right now are the main cause of death worldwide, and it is estimated that more than 30% of all deaths happen because of cardiovascular disease. So you understand the importance and the interest that there is around this type of problem and how we need to investigate and know more about cardiovascular disease. Moreover, the treatments for a lot of this type of disease are really invasive for the patient and they're not always successful, and that's why like a lot of research is going on in this sense. An example is coronary artery bypass grafts. So basically around your heart, there are coronary arteries, which are in charge of bringing oxygenated blood to the heart. And due to the deposit of fat inside their lumen, they tend to get occluded. So there's a blockage. And when this happens, basically you have a heart attack, so a heart failure. So the most common surgical treatment in this case is doing what is called a bypass graft. So the surgeon takes some arteries or veins from the patient and it uses it to bypass the blockage so that blood can still perfuse the heart. And however, it is estimated that 60% of those grafts fail some years after surgery, and the reasons is still unknown. That's why it's really important to do cardiovascular modeling to help doctors and the clinical community investigate the reasons behind these failures. So another question that you may ask is, why do we need computational models? Where when we develop computational models for the heart and the cardiovascular system, we can do a lot of analysis and a lot of investigations. We can do what if analysis, or doctors can compare, for example, different surgeries, plan different treatments, and also predict how those treatments will perform on the patients. So that's a lot of things that like the clinical community could do with computational models. Moreover, there are a number of information that are really useful and interesting to know, to discover what's happening inside the patient that right now are totally impossible to measure in vivo, or they're really, really invasive. So they're not at the disposal of medical doctors. And another reason that it's more like in the future, but since these computational models are personalized, are patient specific because they're built on data coming from imaging, once computational models will be the standard in a clinical setting, medicine will shift from a paradigm that is based on statistics, how it is now. So like the outcome of your surgeries or the successfulness of a treatment is based on the statistics of past patients, then at that point with computational models, like medicine will be personalized. So every treatment, surgery will be tailored to each patient. So those reasons are to convince you that computational models are really useful for clinicians and they're not meant to substitute doctors, just as a tool for them. So as you can imagine, one of the difficulties of this type of projects is that there are a lot of actors into play that need to collaborate to investigate this type of problem. And as an example, this is like the pipeline of my research project, where there is a recruitment phase and a surgery phase done by medical doctors. And this happens in 2 hospitals in Toronto. And after the patients have been recruited and the surgery has been done, we need to retrieve data from those patients so that we can use them for our models. And this is done by radiologists still at these hospitals. Once we have all the data, these are sent to us, and by us I mean University of Toronto, Politecnico, and CISA. So we, like here, a mathematician, clinic, computational scientist, engineer can do the CFD modeling, and we can go back with the results to the medical community so that they can translate it to the information they need. And so how do we go from the heart to a mathematical model? That's the pipeline we use. It's like 6 steps. So you start from the patient, the sick patient, you perform some medical imaging on them. Usually it's a CT scan and 4D flow MRI. From CT scan, so computed tomography, we're able to reconstruct a 3D model of the vessels of interest. And starting from this 3D model, we can build mesh on it, a volumetric mesh, fine enough so that we can solve a mathematical model on it with finite element modeling. Usually we either use Stokes equation or Navier-Stokes equation, and this allows us to know velocity and pressure point-wise all over our domain. Once we have a mathematical model, we can then extract the results and those hemodynamic indicators in a post-processing phase that are interesting for medical doctors and in the clinical community, like wall shear stress, oscillatory shear index, and these indicators are helpful for them to know exactly what's going on in the patient. So even if this pipeline is really like well oiled, it works well, there are still some problems in some of the steps, and that's where we put our attention on. The first one is in the mathematical modeling phase, and it's related to boundary conditions. So as you may know, the choice of boundary conditions when you set up a computational model is really crucial because a small change in the values of the boundary condition or also in the type of boundary condition you use will change completely your results. So if you do a bad choice in your boundary condition, all your results will be totally useless. You will screw up your models. So the question we ask yourself is, how can we choose boundary condition that can make our model as accurate as possible, so that mimic as best as possible what's happening in our patient? So just a brief recap of boundary conditions that we have. This is one of the geometries I work on, and this is an aortic arch. So it's the vessel that brings blood from the heart. So here where you see the inlet to the rest of the body. And you have one inlet and 4 outlets. So what is usually done is to prescribe an inlet velocity. So you're supposed to know more or less the flow rate velocity of the blood coming in. Then you impose a no-slip condition on the walls, so the velocity equal to 0. And then you have to prescribe some sort of outlet boundary condition. And here you have different choices. One is to use the Dirichlet boundary condition, so either prescribe a specific value for the pressure or for the velocity, but this is not like the best choice because it's really difficult to choose a single value of pressure and velocity, and this does not model really well what's happening inside the cardiovascular system. Another solution is to use Neumann boundary conditions. So you're prescribing a specific value for the stress, and this is similar to mimicking the discharge of blood into a reservoir out of your domain. And the third solution, that it's the most interesting one, is to use lumped parameter networks. So to use electrical circuits to model what's happening outside our system. And you may ask why, but this is like well known to engineers and mathematicians that there is a sort of analogy between the hydraulic domain and the electric domain. So if you have an hydraulic system, you can find an analogy in between the main quantities there, like pressure and flow rate, that have like an analogous in the electrical domain. For example, pressure is similar to voltage and flow rate to current. And once you start this analogy, you see that there is blood viscosity can be assimilated to resistance. So something that goes against the current. So the higher the resistance, the lower the current will be. And so the higher the viscosity, the lower the flow rate. And at the same time, like blood inertia, so the ability of blood to flow even in an absence of a force, is similar to an electric inductance. And the compliance of the wall instead, so how the walls of the vessels are able to enlarge um, when they are exposed to a larger quantity of blood, it's similar to an electrical capacitance. Maybe this like doesn't ring a bell to you, but like I'm an electronic engineer, so that's really interesting and fascinating. And this means that we can use as outlet boundary conditions some simple electrical circuits. And an example, like the simplest one, is to use resistances. And by prescribing resistances, it means that you're not fixing either the pressure or the flow rate at the outlets, but you're just fixing the relationship within them, like with Ohm's law. So, and that's more similar to what's happening inside the body, rather than prescribing just the pressure value or the flow rate value, the velocity value. So from this comes another problem. So how can we choose the correct values for such resistances? As you may know, like since these are outlet boundary conditions, if we choose the wrong values for those resistances, this will affect our whole model. What is done in literature is generally to use some values present in literature, so they're not patient-specific, or use some simple rule of thumb to assign them, but this is obviously not an optimal choice. So from this, I want to evidence another problem that it's in the pipeline. It's in a different step, but it's actually related to the boundary condition problem. So when we perform medical imaging, we retrieve a lot of information from the patient, not just from the CT scan where we build a 3D model, but we also perform 4D flow MRI, so a type of magnetic resonance imaging, where we get a lot of information on the specific flow rate of the patient. And this is useful information. So we want to find a way to insert this data into our model to make it as accurate as possible. So to mimic as much as possible the real situation inside our patient, our case. So that's the second question we ask ourselves. How can we assimilate those data and make the model as accurate as possible? So a few details about the imaging process that we're talking about is called the 4D flow MRI, and it's a really advanced type of magnetic resonance imaging. Is not even that common around the world, not in Italy, for example, but in Canada, this type of analysis has been done in Toronto. It's legal, it's done, and it's basically able to recover the spatial evolution of the 3D blood flow into the area of interest, and also its temporal evolution. So it's like having a recording of how the blood flows in the region of interest, and in a 3D way. So as you can imagine, you get a lot of information of how the blood is flowing, the velocity there. It's a lot of data that we can include. So the problem of including data into mathematical models is not new, and there is a whole branch of mathematics that takes care of that, and it's called data assimilation. Data assimilation is exactly the process of inserting data that come from nature, so what we call observations, in our case, our patient-specific data, into a mathematical model, so that the model in the end will be as close as possible to what's happening in real life, like the system you're modeling, but still it's a mathematical model, so you have a physical description of the phenomenon going on. And there are different techniques to do data assimilation that are popular also in cardiovascular modeling. One, for example, is a Kalman filter. But what we decided to use, what we're interested in is optimal control. So optimal control is basically the solution of a problem which consists of a cost functional that must be minimized, and this cost functional is constrained to the solution of a PDE problem. Oh wait, that's an error, it's not Stokes equation, I changed it, it's Laplace equation. But it's constrained to the solution of a PDE problem. And how can you minimize the cost function while solving the PDE problem is by defining a control function that is usually an unknown variable of your system, and you can twitch that. So you can change that in such a way that the cost functional is minimized. Optimal control is really popular in data simulation. It can be used for data simulation. How? Basically, you if you define the cost functional such that you're minimizing the difference between your state variable y and the set of measurement data yd that you got from nature, from real life, you're looking for the solution of your system, of your state equation that comes as close as possible to those data. And that's how optimal control was used for data simulation. So that's really convenient for our problem, and that's how we apply to our case. So we can still minimize a cost functional where we insert our patient-specific data, our data. So there are 4D flow MRI data, and there is the average pressure of the patient that we know. And this is constrained to state equations that we choose to be Stokes equations. The cost control function that we chose is the value of the outlet resistances. So it's the control U. And this means that we are tackling, let's say, both problems that I introduced to you before in one shot. So we are both using the patient-specific data that we need to insert into our model, doing data simulation, but we're also letting the optimal control choose for our outlet boundary conditions. So we don't have to do it. We're not left with the expensive and prone to error phases of manual tuning of the resistances, but this is taken care of by the optimal control. So to give you a bit more details on the optimal control problem that we solved, we define a cost functional here, and that is constrained to the solution of Stokes problem. So the cost functional has a term where we are minimizing the difference between the pressure, the state pressure, and a measured pressure, PD. Actually, we have the average pressure measured on the patient, but we assume to having measured it on a specific cross-section of the aorta. And then here we are minimizing the difference between the flow rates measured with 4D flow MRI, and these are depicted here as the blue dashed lines. So we measure them at all the outlets, and the flow rates that instead is found by the state problem. So the integral of the velocity over the outlet surfaces. As you can see, the terms in the cost functional are both normalized. That's because we wanted all the information, all the data that we had to play the same role into our minimization problem. So they had all the same importance. Let's say we wanted them to be assimilated all in the same way, but we also introduced these weights, so alpha p and alpha I, and we fix them to 1 for this reason. But if you have, let's assume, some data that you are more that you want to assimilate more, that you want to give more importance, you just need to give them a higher weight, and they will play a more important role in the minimization phase. And that's in the optimization phase. And that's the Stokes equation that we're solving. So we prescribe the velocity at the inlet that was also measured with 4D flow MRI, and we take the average value since we're solving a Stokes problem, a steady Stokes problem. And at the outlets, we prescribed resistance values or resistors. And this is something new because optimal control up to now was done with the Dirichlet control or Neumann control. So it had never been done with the lumped parameter networks. So we had to, we took the method developed in this paper to do the multi-scale modeling and connect the lumped parameter networks as outlet boundary conditions to 3D models of cardiovascular systems, and we built the optimal control on top of that. So a few details on how we solve the problem. So we use the adjoint-based Lagrangian approach, which is able to transform our constraint minimization problem into an unconstrained minimization. So you define a Lagrangian functional, which is equal to the cost functional plus the state, the terms of the state equations. And you need to find a minimum of that Lagrangian functional. So you basically define an optimality system that is composed of all the derivatives of the Lagrangian functional with respect to all its variables. And by solving this optimality system, so solving for the solution where all the derivatives are equal to 0, you find the solution of the problem, the optimal solution. And we also use an optimize and discretize approach. So we first optimize the system and then we discretized it. For the actual implementation, we use 2 open source libraries, Phoenix and Multiphenix. In particular, Multiphenix is developed, as you all know, I think, developed at CISA MATLAB. So before showing you the results on how optimal control performed on our patient-specific cases, I just want to introduce to you some alternative methods that are used in the literature for boundary condition estimation. The first one is based on Murray's law. So Murray's law was formulated in 1926, and it basically says that our cardiovascular system works based on a minimum energy principle, so that our vessels are constructed in a way that blood can flow with a minimum amount of work. And that has been proved to be true not only for our cardiovascular system, so that actually like the radii of our vessels are such that our heart needs to do the minimum amount of work to push blood through our body. But it's also true in a lot of other biological systems, like the roots of the trees and so on. And if you translate this Murray's law into the problem that we have for boundary condition, it basically says that the flow at each outlet will be proportional to its cross-sectional area. So it's quite intuitive. The higher the vessel, the more flow will go there. And what's interesting is that this principle for splitting the resistances is based solely on the patient geometry. You just need to know the areas of the outlets, and basically you're done. You don't need to know exactly how the flow splits in the patient, so you don't need patient-specific information. So in order to apply Murray's law, you need first to calculate the total resistance of your aorta, and this means knowing the pressure, an estimate of the pressure over your geometry, and the inlet flow rate, so Q in, and the total resistance, this is Ohm's law, will be equal to the pressure over the flow rate. And once you have this, you can just split the resistances based on the outlet areas. And this is probably by far the most diffuse technique for boundary condition estimation. The second one instead, that is also quite popular, is still uses the analogy with electrical circuits, and it is based on Ohm's law. So in this case, you need flow rate measurements at all the outlets. So you're doing a sort of like data simulation, and the outlet resistance, so assume you can retrieve, like with 4D Flow MRI, the flow rates at all the outlets, so Q1, Q2, Q3, and Q4, and then the resistance at each outlet will be equal to an estimate of the pressure over the flow rates. However, there's an intrinsic problem with the flow rates that you measure from different techniques, from 4D Flow MRI data, for example, is that they often violate mass conservation principle. And this is due mainly to the uncertainty of the measurements. It's expected, is acceptable, but this means that if you sum up like all the flow rates at the outlets, you will not get the flow rate at the inlet. So there's a significant errors inside these measurements. And if you use this version of Ohm's law, this will reflect in a poor choice of resistance boundary conditions. So what we decided to do was to use an optimized version of Ohm's law, so an optimization based on Ohm's law, where we basically solve a simple minimization problem based on Ohm's law that tries at the same time to impose mass conservation principle. So we are minimizing on one side the difference between the measured pressure and the computed pressure with Ohm's law, and on the other, the flow rates at the outlet, measured one and the computed one. And this ensures that we are trying to minimize the difference between some of the outlets and the inlets. So what we did to compare how well our optimal control was performing with respect to what's available in the literature was to solve the optimal control problem and to retrieve like the resistance value at the outlet, and also solve a Stokes problem with all these techniques to find boundary conditions. So we use these three different techniques to find boundary conditions. We solve the Stokes problem on the same geometry, and we compared all the different techniques. So now I can show you the results. We tested our framework, optimal control framework, on 4 different patients. And the results are really consistent one with the other. So I will show all 4, but basically the conclusions are the same. You see here, you have on the first line the measurements for the flow and for the pressure. And here you have the results that you get using boundary condition chosen with different techniques. And the last one is with the optimal control. And you see how optimal control is working better than all the other techniques. One thing that I want to point out is that when measurements when measurements violate mass conservation principle, you cannot expect to have a 0% error on all the outlets, on all the measurements, because the data that you are simulating are intrinsically wrong, like non-physical, while when you solve optimal control, you are solving a physical, like you're finding a physical solution. So you will find a solution that is as close as possible to those measurements, but while still being physically sound. And if we look at the other cases, this is like a 9th patient, you see how in this case, like the starting data were really precise, and we're able to get basically 0 error everywhere. The same happens more or less with Ohm's law and the optimized version. Instead, Murray's law, and it is true for all the cases, is the one that is like the worst technique. It's the one that diverges more from the measurements. This makes sense because Murray's law does not know how flow splits in the patient, but still, like, it's meaningful that it's the most common technique in bioengineering, and it's the worst one. Here, like, still in another patient, case 10, you see how the errors are really good. It's basically 0% everywhere. And the same in case 11, which instead had a huge violation in the mass conservation. And still, like, the optimal control is the best technique. So these results are really good because they show how optimal control works well and is able to assimilate well our data, and it performs better than other techniques, competitive techniques. But still, like, it's not enough if we want to if we want really to have solutions that are interesting for the medical community. In fact, in this case, it's like when you simulate, for example, an aortic arch, you need simulations that must be accurate and high fidelity. And this means they must be necessarily time dependent. And they also need to take into consideration the turbulent nature of the blood there. So you need to have a non-linear model, so a Navier-Stokes model. Moreover, we need to compute all those hemodynamic indicators like wall shear stress, oscillatory shear index, that are those that are interesting for medical doctors. And this can be computed only on, like, high fidelity, unsteady Navier-Stokes simulations. So what we did was to use the resistances that were previously found as boundary conditions and use them as boundary conditions for unsteady Navier-Stokes simulations. In this case, we use as a software for the simulation Vascular, which is an open source software developed at Stanford for high fidelity Navier-Stokes simulations. And I will show here the results for Navier-Stokes. You see that the errors, here I plotted the relative errors of each of the flow rates and the pressure for each case with respect to the measured data. And as you can see, the errors, the distances are a bit higher than for Stokes problems. So I don't have like 0% everywhere, but this is kind of expected because I'm solving a different problem, more complicated one with the nonlinearities, Navier-Stokes, and they're also like time-dependent values. So it's fine, but still the main trends are the same. So Murray, the red one, is the worst everywhere, and the optimal control is either comparable to Ohm's law or better. So that's good. And that means that our choice to do an optimal control framework based on Stokes equation, steady Stokes equation that was lower cost with respect to Navier-Stokes, still it's a choice that pays well, because even when you move to more complicated simulations, the choice that you made with boundary conditions is still good. And last results that I want to show you just give you an idea of how crucial it is to choose proper boundary conditions when it comes then to hemodynamic indicators. So I plotted here for case 10 the wall shear stress that I obtained with the different techniques, so with optimal control, Murray's law, and optimization based on Ohm's law. Then I took optimal control as the reference, and I plotted here the relative difference with respect to optimal control. And you see in this case that you obtain a difference with respect to optimal control in wall shear stress that is almost 30%. And interestingly, the highest one, like the highest point, is here at this exit that is called the left subclavian, L sub, and it is exactly where we have the highest difference in like the highest error in the flow rate. So there is a clear correlation between boundary conditions and the wall shear stress oscillatory shear index that we get. And if we look at the oscillatory shear index, it's another quantity, and it's fixed between 0 and 0.5, you see that the differences reach like 65%. So a small difference in the choice of boundary conditions make a huge impact on hemodynamic indicators. And here I have another case 11. Here, still the wall shear stress reaches a difference of 47%, so it's high. And the oscillatory shear index as well reaches 74%. So that's to prove how important it is to have a method that is automated to choose boundary conditions, so that it's not operator dependent, it's not based on manual tuning, and because that will make a huge impact on the quantities that then will be used by medical doctors to analyze the situation of our patients, choose treatments, and so on. So to conclude, I presented to you today an optimal control framework that is used for automatic tuning of outlet resistive boundary conditions. And this is a point of novelty because there is no optimal control right now that chooses for lumped parameter network boundary conditions. And we're also simulated data coming for the Flow MRI measurements. This is also new because up to now, optimal control was mainly done with synthetic data, so data created artificially, but they were not coming from a real clinical scenario. And we also tested it on 4 patient anatomies, so we are sure it's it works consistently also in different cases. And what I think is great about optimal control is that it gives you such a general framework that it's applicable to a large number of cases that are different, because the whole structure of optimal control, that is this minimization of the functional constraint to the PD problem, can be really applied to different domains, like different part of the cardiovascular system with basically little adaptation. And that's I hope, like we hope, this work is able to show how we can apply, we can move such mathematically advanced and sophisticated techniques such as optimal control to a real clinical, to a real problem, a real clinical setting. So that's all from my side, and I hope you enjoyed this talk. And if you have any question, please feel free to ask.
Thank you very much, Elisa, for this very nice talk. I really enjoyed it. So now it's question time. So if you have questions for Elisa, you can unmute yourself and ask directly to Elisa. Let's see if someone has a question, but maybe I can start with some questions. Actually, Elisa, this talk was really nice, and I have a lot of curiosity to ask. So first of all, yes, this is actually my fault. I really lost, like in the table of your results. Okay, there are all these acronyms like VCA, LCC.
Oh, yes.
What are they? Can you explain it to me?
Yeah, they are the names of the. Actually, there was a figure before.
Okay, so they are the various exits.
The name of the outlets you see here. BCA. Oh, wait. BCA, LCC, they are the names of the outlets. So it's where we measured the flow rate in our patients. And so the data we assimilate, and then we are seeing how optimal control is able to mimic them. And so we computed the distance between the results obtained with the optimal control or with the other techniques with respect to the actual measurements.
Okay, so can I ask a question here? Like, if you have like a guess about the fact that optimal control, it's always, let's say, has always a worse behavior in the AO, right? In the sense that you see that basically you have something like an error that is of 20%. It's quite higher with respect to the others in the exit down, right?
Yes.
So do you have a guess about this behavior? Or it's something
yeah, it's mainly due to the fact of the violation of mass conservation. So the measurements here lack like a 15% of mass that disappears, and when you solve the problem, that 20% mass must go somewhere, and where it goes basically is in the descending aorta, because we are forcing, like, since these are quite accurate, so we are able to mimic that, but there is this amount of mass that we lost and that must go somewhere, and it goes in the descending aorta, and that's why the highest error is there.
Okay, cool. And I have another question about the measurements. I mean, you already answered to that. Oh, actually, there is also a question from the audience. So maybe I can do this last question and then move to the audience. How reliable are these data? In the sense that, as you said, the measurements can be noisy or not physical. So you have taken these measurements, but were they somehow pre-processed by others, or?
Yeah, so the measurements were taken by radiologists, and there was like a denoising phase, and they treated the data before I accessed them, but still the literature for the Flow MRI data says that up to 10-50% of mass violation is perfectly acceptable, and it's coherent with the limitations of the imaging technique. So you cannot expect, like, if you get that, it means it's fine. They're still acceptable. Yeah, so it's intrinsic in the measurements.
Thank you. So actually, we have a lot of questions from the audience. I will go, let's say alphabetically. So Professor Kanjani, you can unmute yourself.
Yes, hi, thanks. I was not the first to raise hand, but thanks anyway. I have a lot of questions as well. The first is if you can say a bit more about the setup of the optimization problem in the Navier-Stokes case. You said that in the Stokes case, you take an average of the flow and then use that. I was wondering what is the setup in the time-dependent Navier-Stokes case?
Okay, so yeah, maybe I didn't clarify that, but what we did was to take the results of the optimal control in the Stokes case and then solve Navier-Stokes simulations without any type of optimal control. It's just a Navier-Stokes simulation with the results obtained with optimal control in the Stokes.
I see. This is what I thought you would be doing, but then in your later slides, you seem to show an error on the on the results of yes. Oh, no, before.
Yeah, that's
no before
that's,
this. The one before this. Yes. So this is not. So this is the error in
so
fact.
that's the
Yes, please.
Yeah, that's the error between the measurements, like the flow rates that I obtained with the Navier-Stokes simulation and the measurement with 4D Flow MRI. So I check if they're still able to mimic those, or if I lose the data simulation properties that I obtained with the before. So
yeah.
just the error with respect to the measurements.
Thanks. Okay, that's more clear. And I'm curious if if you have many outlets like that, isn't there a problem of maybe of uniqueness of possible like results of your optimization? But I'm not an optimization person, so I don't know.
Yeah, for the experiments that we did, I think like we see that we didn't have a problem of multiple solution. It seems that there was like only one solution that can accommodate all our measurements. But about the uniqueness of optimal control solutions, like I'm not super confident on that. So.
Thanks. And did you also consider the case where you don't have well, it doesn't matter. I'll leave to. There's so many questions. I don't want to take all the time. Please.
Thank you.
Okay. So actually, I can comment a little bit. I don't think that the solution, there is a problem with the solution, even with multiple controls. But yes, I don't think that this was, the point of the whole results, and sorry for this precision. So Anna, if you want.
Yeah, thank you very much, Elisa, for a very interesting talk. I wanted to ask you about computational cost of your data simulation method. So is it expensive to perform this Lagrangian optimization?
Well, it's definitely more expensive than solving just a simple Stokes problem. I can give you like details on my simulations, how much they cost. So I solved this on a cluster, and they take up a lot of nodes. It's like 18 nodes, but just like the whole simulation will last like 15 minutes. So it's really fast. It's just a big problem that takes up a lot of space, but then it just converges really fast. So yeah, you need to have a lot of computational power, but then it will be like the solution of the Stokes problem will be fast.
You can do it in parallel, right?
Yeah, it's parallelized.
Okay. But so do I understand correctly that you need to, in order to estimate all these derivatives, you need kind of like a multiple runs of your simulation?
Yeah, so basically the way we solve the optimal control is one shot. So you create the system, your optimality system, that is the system of all these conditions, and then you will look for the solution of all the variables in your system that satisfy the equations. But still there is an iterative iterative solutions going on to find the minimum of the problem. Yeah.
I see. But do you have also any uncertainty in your measurements from, like you said, from nature, from physical world? Do you account for any uncertainties in this data?
Yeah, I know that there are uncertainties in the data, but we didn't do any type of uncertainty quantification or this type of thing. We know that there is an intrinsic noise, intrinsic uncertainty, and that's it. We didn't do uncertainty quantification, or that's what you asked.
So yeah, I know there are many questions, but if I can just quickly comment on it, because for similar problem to find the optimal values of some uncertain parameters, we use, let's say, inverse uncertainty quantification methods. And in this way, we are able to account for this uncertainty in the data. And at the same time, we also kind of measure the uncertainty in these parameters. So we don't only obtain values of the optimal values of these uncertain parameters, but also the uncertainty. So like maybe you will be also interested to watch some Markov chain Monte Carlo approaches for this problem. But
it will be a nice development to know also how the uncertainties of the measurements affect the solutions of our problem. We didn't do it right now, but it could be a future development of this work for sure.
Yeah, I only want to say that this method suffers from computational costs, and this is why I was curious whether it's maybe you're already dealing with this problem. So yeah, but thank you very much. Very interesting work.
Thank you for the questions.
So the next one in my list is Federico.
Ciao, Elisa. Thank you for the very nice talk. I have just two very quick curiosities. So the first one is regarding, again, the tables that you showed. So the fact is that, say, from the medical standpoint, it happens sometimes that they ask you to have, between all these this kind of, say, methods, that the doctors ask you to have a consistent way to underestimate or overestimate some measurement. So because as I can see here, just somehow you have, say, a greater measurement with respect, say, greater value with respect to the measurement, or a lower one. But say there are some times that they need you, okay, I just need that this value have to be much, say, more than some particular one. So say, like, if say you, as you can see, for the Murray's law, you have an error, a percentage error that is, say, negative, no? So you have an underestimation, while for the optimal control value, you have an overestimation. So sometimes, so there is, say, a need for a consistent under or overestimation.
I'm not sure I got the question. So you mean if I can choose, like if I can force the overestimation or the underestimation?
Yes, exactly.
I don't think I can force it. Like I just provide the data to the optimal control, and it will choose like the best solution. I can tell you why here there is like a negative error, like a underestimation or an overestimation in some cases, because the flow rate is not really coherent with Murray's law. So if you look at the areas, so you would expect with Murray's law like a way larger flow rate, and instead we measure the lower flow rate. But I don't know if I can force the estimation.
So there is also, so there is not a need from the doctors to have this kind of, say, stable data in some sense.
No, they never asked us that. I think they will benefit from having a technique that it's stable and it's automated. So you just click a button and it will choose the condition for you, instead of having, like right now it's manual tuning. So they choose the resistance and they change them by hand to match the data that they measured, and that's really operator dependent. That's really expensive because you have to redo the simulations over and over again. That's why, that's the main problems we wanted to tackle.
I see. And instead, the second question is more related with the mass conservation problem that also Maria was pointing out for the last for the optimal control. Say, is there a way instead in which you can say add a term on your optimization functional in order to recover somehow instead this mass conservation regarding the resistance at the outlet? So adding another term to your Lagrangian.
Oh, I see. To insert the uncertainty given by the mass conservation, or I never thought about that. Maybe it's possible, but the fact is that optimal control will still choose a solution that is that follows mass conservation, because the solution will be physical. So either maybe you can work on the measurements before and find a way to maybe to post-process them in a better way, or to denoise them better, so that they yeah.
I see. Okay, thank you.
Thank you.
Okay, we have another question by Doug Crowson.
Hi, Elisa.
Hi.
Great talk. I've got a couple questions. So I'm sure I missed this first part, but it looks to me that your boundary condition for your 3D flow is just this Ohm's law boundary condition, but you've instead got an optimization on the resistance, which ensures mass conservation. So I'm wondering, where does the patient data come into this boundary condition?
You mean in the Ohm's law and the optimization based on Ohm's law?
Yeah.
Okay, so you have here the pressure that is measured on the patient, and also the flow rates, the one that I'm assimilating in the also in optimal control, are used here in the optimization, while this is these are the unknowns. So the resistances are I and no, this is not an. This is the unknowns, and you're solving this optimization problem for these 4 unknowns, and you're trying to match the flow rates. So the pressure of the resistance is the flow rate, the outlets, to the values that you measured.
Okay, so to solve this optimization problem, you just need, per patient, you just need one 4D MRI scan.
Exactly, yeah. And from this you can separate like the flow rates, and this is really easy to optimize just with, we did it with F-mean search in MATLAB, so it's inexpensive.
And so I suppose, do you see that after you solve this, do you see that the flow rates at your outlets do actually match the flow rates from the 4D MRI?
Yeah, they're quite good. And then they're basically the same that you get here, because it's even if you move to Stokes 3D, what you get is basically this. So they kind of match it, yeah.
But are those just different models, or are those actual measurements from the patients?
Like, these are actual measurements from the patients. This is the solution of a Stokes problems where the resistances were chosen with this method. So the resistances that I got there, I solved the Stokes problem where the boundary conditions were these, and then I measured the flow rates at the outlets, and I got these.
Okay. And so my second question is about your lumped network.
Okay.
So so at your outlets, do you have a closed loop? So do they feed back into your inlet boundary?
Oh, for now,
yeah.
Okay, for now, not. They just go to ground, so it's there is no feedback. There are more complicated lamp parameter networks where you also have at the inlet, instead of prescribing the velocity, you have another circuit that simulates the heart, the beating of the heart, and you can close the feedback loop. That's like really, it's really good. You will get really good simulation results, but it means you have to choose way many more parameters for your by your optimal control. So that's more advanced than what we did. This is like the first step for choosing lamp parameter networks, just simple resistances. And there you will have like capacitors and yeah, it's a lot of parameters.
So you need a
complicated.
terminal condition if you're going to ground, don't you?
What do you mean by
Basically,
terminal?
basically a boundary condition at your ground point for your lumped network.
Yeah, that is taken care of by the multi-scale modeling here. Like it takes care of solving for the matching of the 3D to the 0D and to model like the discharge to ground to the rest of the body with no feedback.
Okay.
There's also like an advanced version for this where they simulate instead the feedback loop, so we will have more terms in the formulation. And
yeah. Okay. Thank you.
Thank you.
So it seems to me that there are no more questions. So I thank again Elisa for this talk.
Thank you.
And we will see each other to the next AJS in 2 weeks. So thank you again.
Thank you.